Hello, and welcome to Physics 1101. Today's lab will be focusing on constant velocity motion. Constant velocity motion is motion in which the speed has a constant magnitude and direction. There's no change in the direction, no speeding up, no stopping, or slowing down. I began the lab by recording a lacrosse ball rolling across a semi-frictionless surface. I used my roommate to roll the ball gently across the table. I chose this table because it would be least likely to implement an outside friction force that would slow the ball down and create a non-constant velocity. I then shortened the video to a time that would be easiest observable and most likely to have constant velocity motion. I then set the diameter of the ball to be 63 centimeters. This gives the program a frame of reference to determine the distance traveled by the ball. I then recorded the ball's center of mass frame by frame, and then it showed the entire change in position of the ball over time. The values that show the change in position over time can be seen over here. Let's move on to my Python code, or the modeled values. This code consists of two parts: the initial conditions, which we must set, and the loop, which will do the calculations to predict the ball's new velocity and new position as time changes. Let's look at the first portion, or the initial conditions first. The initial position can be set as 0, 0, 0, since the ball has yet to move in our observations. Time can also be set at 0. We must choose a delta t, or a change in time, a time step, for our observations. Delta t must be very small so that our predictions may be most accurate. For this, we chose 0.01 seconds. We must also know the mass of the ball to be 0.14 kilograms, which can be found on Wikipedia. We also have to determine the initial velocity. For this value, we can go back to Tracker and do a velocity equals the change in distance over the change in time. We can see the change in distance to be approximately 0.22 minus 0.003. And the change in time to be 0.033 minus 0. This will result in a velocity of 0.576 meters per second in the positive x direction. Next, we may look at the loop portion of the code, or the portion that will be determining the new velocity and the new ball position. This mainly consists of two equations: the velocity equation and the position equation, which can be seen here. Velocity equation is v final is v initial plus the net force of the object divided by the mass times the delta t. The final position of the object is determined by the initial position plus the velocity times the delta t. Now you may be wondering where the net force plays into all of this. Well, it doesn't. Since force is equal to the mass times acceleration, and our acceleration is 0, the force is 0. This means that our v final is actually equal to our v initial. Constant velocity. In this equation, for finding the final velocity, the net force is 0, making the final velocity always equal to the initial velocity. There is no change, allowing the ball to have constant forward motion. Now let's go back to the code and run it. When we run the code, it outputs a model of the ball's motion and graphs the position of the ball over time. Here you can see the ball's motion and the graph of its distance over time. We can compare our model data using Excel to the data that we see in the experiment. We can see that the two graphs are only slightly off. This is because constant velocity is hard to achieve in the real world. There are almost always outside forces acting on the object in the world, which will cause the velocity of the ball to change. But for now, our values are close enough for the model to be an accurate representation of constant velocity in our outside world. Thank you for your time.